Hi, everyone. Just wanted to continue this discussion about descriptive statistics, data analysis, point estimation. I hope that your weekend went well, that you were able to enjoy some semblance of normalcy to some extent with Easter, see some family. But let's go ahead and continue talking about this stuff. So I wanted to mention briefly one more time the issue of histograms. And I know last time I had talked a little bit about the rule of thumb where you can determine roughly the number of classes that you want to have. Remember, classes are the width of the intervals that you are going to count the number of data points in there. And remember, you either had a frequency distribution, which you just count the number, and that's like the Y value, the height of the bar, or a relative frequency. And relative frequency is the preferred Y value, okay? Relative frequency is the percentage of data that fall into each one of those classes. And if you have some classes that are kind of smallish, then what you want to do is you want to actually adjust the height of that thing to account for that. You want to make the class width wider so that you get more points. And I mentioned that this was a formula for how to adjust the rectangle height. You go the relative frequency divided by the class width. In fact, I kind of recommend that you do that all the time, and here's why. You want the area of each one of those rectangles to correspond to probability, okay? But in order for that area to correspond to probability, it needs to just straight up equal the relative frequency. So how am I going to have that happen? Well, you know that the width of the rectangle is the class width, okay? And so you would need the class width times whatever the height is to be equal to the relative frequency. Well, that's only going to happen if the rectangle height is equal to the relative frequency divided by the class width. So look, I mean, just multiply through by class width, and you're going to have rectangle height times class width equaling relative frequency. Therefore, the rectangle height should be relative frequency divided by class width. Really, I think it's best to do that all the time so that the area of your rectangles in your histogram corresponds to the probability of falling into each one of those. And that's the essence of what we've been doing with like continuous random variables anyways. Area under the density curve corresponds to probabilities. So I just wanted to mention that in passing here. So we went through all this stuff. Oh, I talked about kind of this empirical rule for when it is that we suspect we have a normal distribution. If we get a sample mean and sample variance, and we notice that within sample standard deviation, if I go down and up from the sample mean by 1 standard deviation, I have roughly 68% of the data. And if I go up and down by 2 standard deviations, we have roughly 95%. And then 3 standard deviations up and down from the sample mean, we have almost everything, 99.7%. You suspect that you have a normal bell-shaped curve. Okay, so that's just a little rule of thumb as well. Now I want to talk a little bit more about other ways that you can look at data, collect it, analyze it. Okay. So histogram's probably the most common way to display data in a meaningful way. There's other things called an ogive, which is spelled O-G-I-V-E, which is basically an ogive is essentially like a cumulative distribution function for the histogram. You kind of draw like how much probability have you accumulated so far as you move from left to right. Okay, so an ogive is really just a CDF for the histogram. But let's talk about some other ways to display data. Okay, one way is through a stem and leaf display or stem and leaf plot. The reason that you say stem and leaf is you kind of have this root or a stem that you start with, and then you have these leaves of data that kind of come off those, and you'll see what I mean here in just a minute. So this is an example. You know, that list down there, I haven't listed all of the data values, but just the first several. And what you do is typically I like to, it doesn't have to be ordered, but I like to put them in order in the first place, just so that it's easier to do the stem and leaf plot. Here what we're doing is we've decided that the stem is going to be the tens digit. For the number 4, the tens digit is really 0, okay? So we allow for that by putting like 0, 1, 2, 3, 4, 5, 6. That's all I need. Those are the only tens digits I'm going to need. And then what you do is you say, okay, which of the data values actually start with a 0 in the tens position? Well, there's only one, the number 4. Okay. Then I have 11. That's what the first one. Here, let me get in here and circle this. That's what this first, right? 11. Right, that's what corresponds to this. Of course, the 4 corresponds to this guy right here, and so on and so forth. You can kind of see how this is going to go. The 13, where's the 13? Well, that corresponds to this 3 and this 1. Okay, what you've done is you've kind of put the digit that it starts with, and you list the leaf or the digit that it ends with on the right-hand side next to the corresponding stem, right? So the 1 is the stem and the 3 is the leaf. For 14, the 1 would be the stem and the 4 would be the leaf. And you just kind of pile up your data values this way. What this does is it kind of gives you like a sideways histogram. You see that? It kind of looks like a histogram here, right? Okay, so you get sort of like a sideways looking histogram. In fact, I've heard statisticians call these basically a dirty histogram. You just it's a quick way to generate a histogram without having to do all of the legwork of doing class width and whatnot. Okay. So by the way, you don't have to use just the tens digit. You can be flexible with this. For instance, here's an example where we have data values. Where you have a bunch of 4-digit numbers. It probably would have been a disaster to like just have the thousands position, because look, we have a lot of data values. There would have only been starting with a 6 or starting with a 7. That would have been too crude. You would have just had 2 huge blocks. So what you can do instead is you can make your stem a little bit deeper into the digits, okay? And you can maybe say that the stem is the thousands and hundreds digits kind of slapped together. So if you do that, then what happens? Okay, so you have the thousands and the hundreds digits serving as the stem in this case. That kind of was going to spread things out. And you say, well, it looks like 6-4 is the smallest and 7-2 is the largest. You list them all. Okay, even ones that don't have any data values, by the way. So if there was none that started with a 6-6, you would still put it there. You just wouldn't have any leaves. Okay, you want to list like empty boxes, just like you would for a histogram as well. You would have little gaps in your distribution where it would go down to 0 for a while and then start going back up. So you want to even list stems that don't have any leaves, just for completeness sake. All right, so 6-4-3-5, of course that corresponds, right? 6-4, the 3-5, that corresponds to this first data value right here, okay? And you go down and you list this thing and you get your nice quick histogram when you do that. There's kind of the sideways histogram by way of a stem and leaf plot, okay? It's possible, incidentally, a histogram, a stem and leaf diagram, all of these things are possible to generate in Excel. I think if you go to like insert, one of the options is to do like a histogram, and I think there may even be a way to do a stem and leaf plot. But it's typically fairly difficult until you install a special data analysis package, and then those things are kind of built into it. But these things are easy enough to make by hand. So. Okay, so let's construct, there's another kind of a stem and leaf diagram, which is comparative data analysis, where you basically want to look at 2 distributions at once, okay? And the stem and leaf plot is one way to do that quickly. What you do is you essentially line up, but you decide what your stems are going to be, and then you put the leaves for the one data set in the one direction, and you put the leaves for the other data set in the other direction. Okay, so what are we going to do here? Well, it looks to me like what the smart thing to do would be, look, if we just did 9, or if we just did like the first digit, like 0, like, you know, the 90s and 110s and whatnot, well, actually that might work out okay. So let's actually do that here. So what are we going to have? Let's put the American data on the left, and let's put the French data on the right. Oops, French data on the right. Okay. And what is our stem going to be? Well, let's go like this. So this is the stem. Okay, stem. So what we're going to do, let's go ahead and do the tens position and the hundreds position. So that would mean I would have 0, 9, 1, 0, 1, 1, and maybe 1, 2. Is there any things that are higher? There actually are. Okay, there's 1, 3. Okay, there's actually several more. So 1, 4, 1, 5, and 1, 6. Is there anything higher than 1, 6? I think that's about it. Okay, so for the French, what do we have here? I have a 90. Okay, so I indicate that by putting the 0 here. So that gets rid of this. There's another 90 right here. Okay, there is a 94. Like I said, I like to do these in order when I'm doing this sort of thing. So let's see, 94 would be next. Okay, what else? 96. And I think that does it for the 90s on the French side. Let's look at the American side. Okay, I see a 90. Okay, so there's a 0 right there. I see a 91. Oh, oops, I see another 90 actually down here. There's a 91. Okay, what else? Let's see, there is a 94 right here. Okay, there is a 90, there's two 95s actually. Okay. And actually I see that I actually need an 80 here because of the American side of things. Okay, so let me put an O. Okay, I know that this has kind of been marked over, but I'll put an 08 right here. And I see that I need an 81. So there was 1 right there, but I didn't have any on the French side. Okay. And let's see here. So I think I've taken care of all the 90s. I just like to count the number of things just to make sure I haven't missed anything. On the French side, I have 1, 2, 3, 4. That's exactly the number of leaves I have there. So again, these guys right here are the stems, and down here I have the leaves. Okay. So let's see here, 1, 2, 3, 4 on the French side. I had one in the 80s, and I had 1, 2, 3, 4, 5, 6 in the 90s. Okay, what about things that start with 1, 0? Okay, things that start with 1, 0 on the American side, I see a 102 and a 104. Okay. What about on the French side? I see a 102. Okay. And I think that's probably it. Okay. What about 1, 1? Well, on the American side, I see 116. Okay. And on the French side, I think that's it for the American side. On the French side, I see a 116 and a 119. So 6 and 9. Okay. What about 1, 2? Well, I see on the American side, I have a 128. Okay. And what's going on with the French side? Well, I see a 128 and a 125. Yes. And notice one thing that's kind of nice is even if I miss one, it doesn't really matter. I'm still stacking things up here. It's not wrong to have an 8th and a 5 rather than a 5 and an 8 or something. Okay. I'm just trying to collect the data in an organized way. Okay, so I have a 128 and a 125. All right, what's going on with the French side? Well, I see a 122, a 123, and a 125. Yeah. Okay. Now, what's going on here? Okay, so looks like on the French side, I have a 137. Okay. And what else? I have a 158. And on the American side, I have a 162. Okay. So I don't know. I mean, you can kind of get a pretty good idea of how this data is collecting here. Or you can compare these two distributions. Looks like overall the American side is bunched up more towards the smaller numbers. And again, these were run times in minutes for American and French movies. So, I mean, if I were staring at this, you know, I would probably say it looks like French movies tend to be longer on the whole. American movies are bunched up towards the 90-minute zone, whereas the French movies tend to be a little bit longer on the whole, it would appear, although there's that one giant length movie down at the bottom, 162 minutes, the longest one of all. But most of the American movies tended to be shorter, okay? All right, so that's how you do a comparative and a quick comparative analysis using a stem and leaf diagram. Let's move on, okay? So let's talk about quartiles and percentiles. We've already talked about percentiles in the context of continuous distributions, and we used the continuous distribution function, or the cumulative distribution function rather, to find percentiles. We used Excel to help us out in some cases to do that. But here we're going to just revisit the notion of percentiles, and specifically we're going to be interested in something called quartiles. So the median divides a data set into two parts of equal size. Remember, if you have an odd number of data points, the median is the number that's exactly in the middle. And if there's an even number of data points, you have to take the average of the middle two numbers, okay? So you have the median dividing the sets into two pieces. Then what you do is you take those two halves, okay? And by the way, if the median is a data value, you kind of exclude that from consideration. You exclude it. And then what you do is you then take the two halves that are left and you find those medians. And when you do that, you'll have the first quartile and the third quartile values. And you'll have split the data into 4 equal parts, okay? So the quartiles divide the data into 4 equal parts. 25% of the data is to the left of Q1, twiddle, right? You have these little tildes on here, okay? Of course, Q2 tilde is the same as the median, mu tilde. Q3, you have 75% of the data below it, okay? And that's it. Of course, here we're dividing things, we're hacking the data up into chunks of size 25%. When we talk about percentiles, cent means 100. So what we're doing there is we are actually splitting up the data into 100 parts of equal size. The first percentile means that 1% is below it, 99% above. Second percentile, 2% below, 98% above, etc. Okay? So the example, like if there's a 99th percentile and you use pi for percentile. Pi tilde, you put a little tilde on there, sub 0.99 means that there is 99% below it and 1% above it, okay? So another tool in the analysis of data is something called a box plot. Sometimes it's called a box and whiskers plot because it looks like a box with some whiskers on it. But a box plot basically takes, again, it's another way of just quickly being able to see what the data looks like. A histogram is really nice, but oftentimes it takes a fair amount of work to actually generate it. We saw that a stem and leaf diagram, you can quickly get the information that you need. You can even compare two data sets very quickly and look at their distribution and decide certain things based on those two comparative distributions. This is another way to do that. A 5-number summary, you basically take the maximum and the minimum, and you take the first quartile, second quartile, and third quartile. Those 5 numbers are a way to kind of summarize the data, and we're going to summarize that visually with those 5 numbers, okay? And there's going to be an important quantity that's going to come up. It's called the interquartile range. The interquartile range is simply just the third quartile minus the first quartile number, okay? So what that basically is it's just telling you how far it is between the 25th percentile and 75th percentile. Really what you're finding is the middle 50% of your data. That's how you're finding the width of the middle 50% of your data. That's what the interquartile range is. Now it turns out that that is going to be important for rigorously defining what it means to be an outlier, okay? And we'll talk about that in just a minute. So 5-number summary, minimum value, maximum value, first, second, and third quartiles. Okay, and with those 5 numbers, you can start to draw the so-called box plot and get an idea of what the shape of your data looks like. Okay, first of all, I want to mention what the interquartile range can tell you. I said it's connected to the concept of outliers and can tell you specifically what you mean by an outlier. Now, people like to say, oh, who cares about that data value? That's an outlier. Well, how do you know it's an outlier? There's a rigorous way to define what an outlier is. And it has to do with using the interquartile range as a gauge for how wildly out of bounds a data value is, okay? So the first thing you do is you take your interquartile range. By the way, you call that IQR. We called it IQR back here, right? So you take IQR, you multiply it by 1.5, right? So IQR is, remember, it's the width of the middle 50% of your data. You take that width, multiply it by 1.5, so you stretch it a little bit, and you go that far above the third quartile, okay, above the 75th percentile. And anything above that is a so-called suspected outlier. Similarly, you go down to the 25th percentile, i.e. the first quartile. You go down by 1.5 interquartile ranges. And anything below that is a suspected outlier. And in fact, it's a flat out outlier if anything that's above 3 IQRs to the right of the 75th percentile Q3, or below, or 3 IQRs below the first quartile, that will be an outlier. Okay, so you have suspected outliers. There's kind of two, anything that's is less than 1.5 IQRs, that's just normal. Okay, anything that's between 1.5 and 3 IQRs, either to the right of the 75th percentile or to the left of the 25th percentile, those are called suspected outliers. And anything that's 3 IQRs to the right of the 75th or to the left of the 25th percentile, those are flat out outliers, pure and simple. Okay. And here's what a box plot looks like. Okay, and you can probably see why it's called a box and whiskers plot. What you do is you kind of just draw, or you put a point at the lowest, smallest value, the minimum, okay? And then you go to the first quartile, Q1, and you draw a vertical line, and you go to the median and you draw a vertical line, and then you go to the third quartile and you draw a vertical line, and then you put a box like this. And of course, this distance between the third quartile and the first quartile, that is the IQR, the interquartile range, okay? And then you label your maximum, okay? And the maximum apparently is up here, okay? And then look, you like draw a line down to the minimum if the minimum isn't like a suspected outlier. And you draw a line out to the last data value that isn't a suspected outlier. But anything that's above, so I mean, I guess what they're saying here is that this is plus 1.5 IQRs, okay? And then at that point, you start suspecting that something's an outlier. But that's above Q3. And of course, I would do the same thing on the left if necessary, okay? And this right here, this is plus 3 IQRs. And these guys out here are all outliers. And you just kind of label them, okay, as such. So, I mean, sometimes you can, what we've done here is we've actually filled in the data values that are suspected outliers, and we've just straight up put little circles at data values that are flat out outliers. But you only put the whisker out to things that are not suspected outliers, okay? But technically the 5-number summary is just the minimum, the Q1, Q2, Q3, and the maximum value, which in this case happens to be an outlier, okay? So that's how you create the box and whisker plot. So, honestly, most of the time you're not gonna really end up with outliers. You'll just, the box and whisker plot will actually encompass all the data. This data is what is positively skewed. It's kind of skewed to the right. You can kind of tell that that's happening if you see the median kind of being dragged or kind of staying to the left while the rest of the data is being dragged downward off to the right. This is a positive skew on the data that we happen to be seeing right here. Okay, so that's interesting. We now have a rigorous way of talking about what it means to be an outlier. Okay. All right. So let's have a peek at this right here. So given the following stem and leaf display, and again, notice, data values always have a stem and a leaf. And you'll notice that like right here, there is nothing. Okay. So, I mean, I don't know why this was sort of listed in this way. So to hundreds and tens, the leaves are the ones position, okay? You would have written a 0 if like 280 would have been in there. But I just want to say that there is no data in that zone and no data in this zone right here, okay? So how am I going to find or first of all, how many data values do we have? Well, there's n equal to, let's count, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. There's 23 total data values, okay? So that means, that Q2, okay, and by the way, what is the smallest data value? Well, that's easy, right? So the min value is actually 316. Okay, you can just read that off directly from this, okay? N equal to 23, I know what Q2, I can figure out what the second quartile is going to be. That's the median. I'm going to want the 12th value, okay? The 12th value. It will have 11 above it and 11 below it. So where is the 12th value? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, it's this guy right here, 334. 334. And let's just make sure, just for good measure, that there's 11 things below it as well, or 11 things above it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Indeed, there are. Okay, so now I have 11 things below and 11 things above. So what am I going to do? Well, I can actually find Q1 twiddle. Okay. So there are 11 things, so I want the 6th value. Okay, what's the 6th value? 1, 2, 3, 4, 5, 6. Okay, so it's that 4 right there. Okay, and as you can see, there's 5 below and above that in that lower half of data. Okay, so that's 324. Okay, and same thing up above. Okay, I have 11 values there, so I want the 6th one. Okay, so that there will be 5 below and 5 above. 1, 2, 3, 4, 5, 6. It's this guy right here. Okay, 5 below and 5 above that guy. So what do I have here? 357. So that's what Q3 tilde is. Okay, 357. Okay. Of course, the maximum value is equal to 445. And what is our IQR? Well, that's Q3 tilde minus Q1 tilde, which is 33. Okay. And what's 1.5 IQR? Well, okay. 1.5 IQR, what is that? Well, that's going to be 33 plus 16. So what is that? That's 33 plus, or sorry, 33 divided by 2. Okay, 33 plus 16 and a half. Okay, so what is that? 49 and a half. Okay. And what is 3 IQRs? Okay, well, that's going to be 99. Okay, 99. So what does that mean? Well, I need to look at what Q3 tilde plus 1.5 IQR is. Okay, so that's going to be, okay, what is Q3? Q3 is 357. Plus what? 49.5. Okay. Okay, so that's going to be 406.5. 406.5. Okay. And what about Q3 tilde plus 3 IQRs? Well, that's going to be 357 plus 99. Okay, which is 456. Anything above that value is a flat out outlier. Okay, but there isn't anything above that value. The largest value we have is 445, but we do have some suspected outliers. Okay, because the maximum is 445. Being above 406.5 makes you a suspected outlier. So that means that 425 and 445, there's a couple of suspected outliers. You know what I mean? Okay, So, and incidentally, I should have also computed Q1 tilde minus 1.5 IQRs. But look, if I go to if I go to 324 and subtract 49.5, I'm already below the minimum. Okay, so I don't even have to worry about suspected outliers on the lower end of things. Okay, so how's this going to work? Well, let me just kind of say that this, okay, this is 316, and then I go up to 324. Okay, so this is 324, and then what's next? 334. Okay, and then 357. Okay, so let's see, like that. Okay, and then I go up to the last thing that isn't a suspected outlier, which would be 392, apparently. Okay, so 392, I don't know, just kind of guesstimating the distance here. So 392. Okay, and then I have to list my suspected outliers. There are two of those. There's 425. And there is 445. 445. Okay, and I kind of like to put a little thing like this, and I like to say, these guys are suspected outliers. Okay, and again, that was just a rough sketch. I would need to be more precise if I wanted to have this thing be perfectly to scale. But this is at least a quick way to kind of summarize the data. Looks like I have a little bit of a positive skew going on here as well. Okay, it's not surprising since I have some suspected outliers out on the right end of this thing. Okay, I think that's all I wanted to cover about exploratory data analysis. This was just, again, I think it's nice to just have this stuff in your cognition as we move forward with some rigorous data analysis. So the next couple of lectures, I'm going to start jumping into applications of the central limit theorem in the context of confidence intervals. And then eventually we will talk about hypothesis testing. That's what we'll finish the semester with. Okay, that's all for now.